The galactic center is the rotational center of the Milky Way. It is located about 8.33 A plus or minus 0.35 kpc from Earth in the direction of the constellations Sagittarius, Ophiuchus, and Scorpius, where the Milky Way appears brightest. There is strong evidence consistent with the existence of a supermassive black hole at the galactic center of the Milky Way. Proof of existence and location: because of interstellar dust along the line of sight, the galactic center cannot be studied at visible, ultraviolet or soft X-ray wavelengths. The available information about the galactic center comes from observations at gamma-ray, hard X-ray, infrared, sub-millimeter and radio wavelengths. Coordinates of the galactic center were first found by Harlow Shapley in his 1918 study of the distribution of the globular clusters. In the equatorial coordinate system they are RA 17 hours 45 M 40.04 S, Deca 29 a degree 00 28.1 inches. Distance to the galactic center: the exact distance between the Solar System and the galactic center is not certain. The latest estimates from geometric-based methods and standard candles yield distances to the galactic center between 7.6 and 8.7 kpc. An accurate determination of the distance to the galactic center as established from variable stars or standard candles is hindered by countless effects, which include an ambiguous reddening law, a bias for smaller values of the distance to the galactic center because of a preferential sampling of stars toward the near side of the galactic bulge owing to interstellar extinction, and an uncertainty in characterizing how a mean distance to a group of variable stars found in the direction of the galactic bulge relates to the distance to the galactic center. The nature of the Milky Way's bar which extends across the galactic center is also actively debated, with estimates for its half-length and orientation spanning between 1 kpc and 10 50 degree. Certain authors advocate that the Milky Way features two distinct bars, one nestled within the other. The bar is delineated by red clump stars, however, Rayleigh variables do not trace a prominent galactic bar. The bar may be surrounded by a ring called the 5 kpc ring that contains a large fraction of the molecular hydrogen present in the Milky Way, as well as most of the Milky Way's star formation activity. Viewed from the Andromeda Galaxy, it would be the brightest feature of the Milky Way. Supermassive black hole. The complex astronomical radio source Sagittarius A appears to be located almost exactly at the galactic center, and contains an intense compact radio source, Sagittarius A, which coincides with a supermassive black hole at the center of the Milky Way. Accretion of gas onto the black hole, probably involving a disk around it, would release energy to power the radio source, itself much larger than the black hole. The latter is too small to see with present instruments. A study in 2008 which linked radio telescopes in Hawaii, Arizona and California measured the diameter of Sagittarius A to be 44 million kilometers. For comparison, the radius of Earth's orbit around the Sun is about 150 million kilometers, whereas the distance of Mercury from the Sun at closest approach is 46 million kilometers. Thus the diameter of the radio source is slightly less than the distance from Mercury to the Sun. Scientists at the Max Planck Institute for Extraterrestrial Physics in Germany using Chilean telescopes have confirmed the existence of a supermassive black hole at the galactic center, on the order of 4.31 million solar masses. Stellar population. The central path around Sagittarius A contains thousands of stars. Although most of them are old red main sequence stars, the galactic center is also rich in massive stars. More than 100 OB and Wolf-Rayet stars have been identified there so far. They seem to have all been formed in a single star formation event a few million years ago. The existence of these relatively young stars was a surprise to experts, who expected the tidal forces from the central black hole to prevent their formation. This paradox of youth is even stronger for stars that are on very tight orbits around Sagittarius A, such as S2 and SO-102. The scenarios invoked to explain this formation involve either star formation in a massive star cluster offset from the galactic center that would have migrated to its current location once formed, or star formation within a massive, compact gas accretion disk around the central black hole. Most of these 100 young, massive stars seem to be concentrated within one or two disks, rather than randomly distributed within the central pask. This observation, however, does not allow definite conclusions to be drawn at this point. Star formation does not seem to be occurring currently at the Galactic Center, although the circumnuclear disk of molecular gas that orbits the Galactic Center at 2 pasks seems a fairly favorable site for star formation. Work presented in 2002 by Anthony Stark and Chris Martin mapping the gas density in a 400 light-year region around the Galactic Center has revealed an accumulating ring with a mass several million times that of the Sun and near the critical density for star formation. He predicts that in approximately 200 million years there will be an episode of starburst in the Galactic Center, with many stars forming rapidly and undergoing supernovae at 100 times the current rate. This starburst may also be accompanied by the formation of galactic jets as matter falls into the central black hole. It is thought that the Milky Way undergoes a starburst of this sort every 500 million years. In addition to the paradox of youth, there is also a conundrum of old age associated with the distribution of the old stars at the Galactic Center. Theoretical models have predicted that the old stars which far outnumber young stars should have a steeply rising density near the black hole, a so-called Pacula-Wolf cusp. Instead, it was discovered in 2009 that the density of the old stars peaks at a distance of roughly 0.5 pask from SGRA, then falls inward. Instead of a dense cluster, there is a hole, or core, around the black hole. Several suggestions have been put forward to explain this puzzling observation, but none is completely satisfactory. For instance, although the black hole would eat stars near it, creating a region of low density, this region would be much smaller than a pask. Because the observed stars are a fraction of the total number, it is theoretically possible that the overall stellar distribution is different than what is observed, although no plausible models of this sort have yet been proposed. Gallery. See also, Galactic Anticenter, Galactic Coordinate System, Great Rift, Sagittarius B2, Supermassive Black Hole, Cosmic Noise, Notes and References. Further reading, Eckhart, A. Paragraph Del, R. Strawberry, See the Black Hole at the Center of the Milky Way. London, Imperial College Press. ISBN A1-86094-567-8. Melia, Fulvio. The Black Hole in the Center of Our Galaxy. Princeton, Princeton University Press. ISBN A0-691-09505-1. Melia, Fulvio. The Galactic Supermassive Black Hole. Princeton, Princeton University Press. ISBN A978-0-691-13129-0. External links, UCLA Galactic Center Group, Max Planck Institute for Extraterrestrial Physics Galactic Center Group, The Galactic Supermassive Black Hole, The Black Hole at the Center of the Milky Way, The Dark Heart of the Milky Way. Animation showing orbits of stars near the center of the Milky Way galaxy, zooming in on the center of the Milky Way, dramatic increase in supernovae explosions looms, APOD, journey to the center of the galaxy, a galactic cloud of antimatter. Fast stars near the Galactic Center, at the center of the Milky Way Galactic Center starscape, annotated Galactic Center. A simulation of the stars orbiting the Milky Way's central massive black hole, Galactic Center on arXiv.org, Milky Way, distance to the Galactic Center, Milky Way, a distance to the Galactic Center, 2, Milky Way, a distance to the Galactic Center, 3.